Hello guys. So I was looking at some videos the other day about using Rust with React Native, and there are a couple of videos out there and a couple of talks which seem to go over some of the high level topics, right? So threads and promises, something where you have already set up your Rust compilation and you can already jump into the more advanced features. But I always find these talks, I mean, they're very interesting, but if you have no idea about the Rust compilation chain, or you're not an expert with Xcode and linkers and so on and so forth, it's always kind of confusing to set it up for the first time. So I thought I would try to set it up for myself, and as usual, run into some troubles. So I thought making a video about it might save time for somebody out there. So what I'm going to do now is I will try to create a Rust compilation target, which I will just call from React Native, from the JavaScript side. This is just going to be the first part of what I expect to be a series of videos, and this is only going to deal with iOS and the old bridge. Just to get the concepts of compilation about Rust and so on. And then later we can move to JSI or turbo modules and so on and so forth. Okay, good. So the first thing I'm going to do, or the first thing that we need to talk, is about Rust. Right, so you need to install Rust on your machine. That's easy to do. The documentation is fine. The next step that you need to do is you need to add the targets for the platforms you're targeting to, right? So you are going to cross compile from your Mac to different targets, macOS, iOS, the iOS simulator, and so on and so forth. So in order to do that, you can just go into your terminal, just clean this, and you will do add rust up target add, and then you just add the architectures that you're going to target. So for this, you're going to need 3 architectures. You're going to need the 64-bit Apple iOS, which is, as far as I understand, for Catalysts and older machines, so the Intel machines. I already have this installed, so it's not going to do anything for me. Then you will also need the Arch 64 Apple iOS for the simulator. If you're on an M1 machine, this is the new architecture of the simulator. And you will also need the Apple iOS, which is the actual target for iPhone models. Good. So once you have all of that, in theory, you are already ready to compile Rust for the iOS architecture. The next thing I'm going to do is I'm just going to create, well, I already have the folder in here, but I'll just delete this one. In my project, 1 second, let me just go back. So I'm going to create one folder. I'm just going to call this my SDK. And inside of my SDK, I am just going to create a new Rust project. So I'm just going to call this the same, my SDK. And you will see here it has been created as a normal Rust project. It has a main function, and if you try to run this, it will just look for the main function. Now, the difference is we don't want to immediately run something from Rust. We want to make this as a library. So we need to start preparing for this. The first thing that we're going to do is we're going to change this to lib. This is all standard Rust. I'm not doing anything fancy, right? You can find this in the documentation. And yeah, before creating the code, let's just go over some of the configuration that we need to do. The first thing that we need to modify is the cargo.toml. And here we're going to change, or we're going to add some keys. So the first thing that we're going to add is a lib section. The name is going to be my SDK, and we're going to give it a crate type. So for iOS, I'm going to use the static lib, right? So this is basically telling Rust compile the code as a static library. For Android, I think it's better to use a dynamic library, or maybe even required. I'm not sure at the moment, but we're just going to cover iOS at the moment. Once that's done, I'm going to add another key, and here I'm going to add the libc dependency. So the libc dependency gives you some types or some objects that you're going to need to use in order to interact between Rust and C, right? So we're going to use C as a bridge between C++, or in our case Objective C++, and Rust. And let me just quickly check to make sure I'm not forgetting anything. Yeah, I think it's fine. Good. Okay, so we can now tell Cargo to build our project. Sorry. Okay, it has created. So I'm going just to move everything to the top folder. It has created a subfolder which we don't need. We can tell Cargo build, and here you can see function main is never used, right? So it can compile, but it's just not going to work the way we are expecting. So this is where we need to talk a little bit about cross-compiling, or compiling Rust to interact with C. Let me just make sure that I am on the right path. Okay. So we're going to go into the lib.rs, and I'm going to declare a couple of the dependencies. So first the libc, which we talked, we're going to need this. So I'm also not an expert on Rust. Maybe there's some other ways to do some of this stuff, but this is just a very basic example, and this is what works for me at the moment. In the future, maybe I'll figure it out a better way. So first I'm going to import these two types. First the C char and the C string. So a C char is just the char type for C, is the unsigned integer, a byte, right? And the C string is the same concept of C strings, like a series of bytes terminated by a null character. So these two will allow us to return these objects into the C world, and C will be able to easily interact with them. Okay, so I'm going to add a function, and first I'm going to put the nom angle. I'm going to talk in a second about it. Then I'm going to create a public unsafe extern. Okay, he did it into me. Good. So let's talk a little bit about Rust and how it can compile to C compatible code. So the first thing you see here is this nom angle declaration. You can think of this as a annotation in JavaScript or Java or whatever. So the nom angle annotation, what's going to tell the Rust compiler is not to mess with the function names, right? So if you would compile Rust directly, it will probably get rid of this function name, and it might replace it for something shorter, right? Like an identifier. You don't need to know about this. This is also what the obfuscators does, and minimizing the JavaScript code, for example. You don't need the entire string of characters, so you can just change it to an identifier. So basically the nom angle is telling the compiler keep the name of the function available. Now there is the extern keyword, which is a little bit more complex. So you have, when you compile a program, besides an API interface, you have what's called the ABI, the application binary interface. So the binary interface is basically how types are mapped into the raw memory, right? So for example, you have, like we talked about, the concept of a C string, right? Like the string is a series of bytes that get terminated by a null character, right? So if your programming language doesn't use the same representation in memory when you're storing data, then if another programming language tries to write or read the same data, it basically has no idea what is it, right? Like it will try to interpret it as a different type or the structure of the type that it knows, and it will basically give you trash. So what we're telling by saying this in the extern keyword is we're telling basically use the C ABI, the C application binary interface. So the types that we return when they map into memory, they can be read by C programs. On safe, this is raw stuff, public, so it can be accessed. And here we have our cchar const, and this is basically, we're telling this returns a pointer, right? So from when we call this function from the C code, we will get a pointer, and then we can just cast it or try to read it as a string, right? So it will read all the bytes until it finds a null character. The code inside is normal Rust. We have a C string, we create it. This gives you a result container. So it can be either result or error, and by using the expectation, if it cannot allocate the string, then it will fail. And basically we're returning the into raw, which is just telling Rust, just return this pointer to the calling function. Good. So now that we have that function, we have this, we can try to compile it, and okay, our TOML is not working. Give me 1 second. Why do I have the duplicate key? Good. So good, it has compiled. So now we can see here we have a target folder, and we have debug compilation target, and this is what we're interested in, the .a file. This is the library file that will be used for iOS, for Xcode. But you can see that we only have one, and we haven't specified any target. So basically we just told Cargo build it, right? So it probably took the target of the machine where I'm running for macOS, and it just compiled it into compatible code, which is not exactly what we want, right? Like we want to generate this .a library file for each one of the architectures that we have added before. So what I'm going to use is makefile. You can use whatever you want. You can use a bash script, but makefiles are designed for this. And also I found a kind of already working implementation on the internet. So what did I do? Okay, let me just copy this. I'm going to go in my SDK folder. I'm going to create a new makefile. Okay, so first I declare a couple of variables. For the Android one we don't care about at the moment, but first I declare all the architectures to which I want to compile my code. So these are the architectures that we added before. Then I'm going to declare the name of my output, the output of the library, and I'm going to declare as well an XC framework. I'm going to tell you why in a second. So first, if I wanted to compile everything for iOS and Android, then you declare the all, and it will run both of these targets. For now, we don't care about Android. And for iOS, I am saying, okay, you need to do this step first, the XC framework step, which is declared here. For the XC framework, is the same thing. First, you need to do the args iOS. And for iOS, is basically a cargo build with my target, so each one of this, and I'm going to compile them in release mode. So it's strips the debug symbols, or whatever debug information that might be there. Okay, so this is a part that was painful because the information on the internet is kind of fragmented. This cargo build is going to generate 3.a library files. If you would try to, or let's say the other way, you can combine different library files into a single .a file, right? So you can just distribute one single file for all the architectures that you were trying to target, right? So you would do this, for example, to distribute one single .a file for Windows, macOS, and Linux, right? And that works fine. But there's a small problem with iOS, because basically this architecture and this architecture are targeting the same processor architecture, ARM 64, right? So when you try to combine these two, the tool, which is called LiPo, it doesn't really know which one to pick, right? Because it can only separate things by architecture, not really by which target you're aiming for. So what we first need to do is we need to bundle the output of this target, the 64-bit normal Intel Apple iOS, and the ARM Apple simulator. These two we can merge into a single .a file. Now the problem comes with the actual iOS release one. And for this, Apple has created a way to distribute these files that target the same architecture without causing conflict. And this is called the Xc frameworks. Right. So what I'm doing first is I am merging these two releases for iOS simulator and Intel into a single FAT, into a single .a. And then I'm taking that FAT library that I've generated and the iOS one and putting it into a single Xc framework file, which we will later export or import into Xcode. Good. So if we now try to compile this, let me see. Can create temporary output. Okay, this is a different error. Give me 1 second. Where is this? Where's my make file? Just copy it one more time. Okay. I'm just going to create one new folder because LiPo cannot create folders on its own. Yeah, so you see these smaller things that you have really no idea about. So I'm going to create a simulator FAT folder. And when I try to run this again, okay, now I get the error I was expecting. We're missing the headers. So Rust, or when you're creating a library, a static library file, you cannot just use it, right? The .a binary file only contains binary information. In order for you to import this code into C and call the functions, you need the header file. Like the header file is basically a map to what are the functions that are exposed in the binary. So there's basically many ways to do this. One way is to manually create your header file. Right, so I could go here and let me just, I'll create another folder. This is also important to create. Xc framework won't do it for you. And I could say here my sdk.h, right? And here I would just declare the function that I just created, hello world, right? So the .a has this available function to be called from the C world. The problem with this is that it's a manual process, right? So every time you change your function, your Rust code, you will need to go inside of the header file and manually edit it. So there are actually better ways to do this, and Rust provides, or there are some Rust crates that allow you to automate this process. One of the tools, or the tool that I'm going to use, is called cbindgen. Let's look for this. cbindgen, right? So cbindgen is basically going to take your Rust code, and depending on the functions that you have declared as external, it's going to automatically generate a header file for C++ and C. The other option is CXX, I think. Yeah, so this is another tool that generates the header files and yeah, all the stuff that you need to generate in order to call your Rust code from C. Yeah, so there are some problems with bindgen and cbindgen, but for now, I mean, this is simple. I'm just going to stick with it and get it to work. So in order to do this, the first thing that I'm going to do is I'm going to do cargo install cbindgen in the project. So this is going to download a bunch of stuff, and once that's done, I need to create one cbindgen .toml file. So cbindgen toml. Give me 1 second. Let me just check and make sure that's right. Yeah. And this can be empty for now. It's fine. I mean, you can customize, what type of headers you want to generate and so on and so forth, but this is so simple that we don't need to do anything else. I can just take the command that I have in the documentation. I will just modify it a little bit, and I'm just going to run it as cbindgen config. I'm just going to point to my empty toml file. The crate that I'm going to generate, this is the name of the header file that I'm going to generate, or the crate that I'm aiming to generate the bindings for, and the output is going to go in the include folder, and this is the name of the file. So if we now go here, you can see that it has imported some includes that you might need. It has created the extern C namespace, and we have finally the function that we have declared on our Rust code. So this takes care of generating the correct bindings for us. So now I can do again make iOS, and it has outputted the Xc framework, right? So here you can see I have my iOS target, and here I have the fat combination of ARM plus the 64 simulator. With the info plist is basically the information that Xcode will use to pick the correct version of the library when you're compiling the application. So that's basically it for the Rust side. Now I can go into Xcode, and in Xcode I am going to use, so for now I'm going to use the old bridge because it's just easier at this point. Of course, if you want to get the most performant, then you need to use JSI or turbo modules, but it doesn't really matter, right? Like once we have compiled everything on Rust, and we can also call Rust from the C code, you can just pick whatever method you want to call this code. So for now, I'm just going to generate a Objective-C file. Yes, and I'm just going to call this bindings. I want to put it in there. I also want a header file. It's going to call it bindings, and this is just the standard. This is just the standard React Native all bridge code. Right. So I'm just declaring a bridge module that will be picked up by React Native. And here I am just going to declare, okay, I'm just going to paste it and then we can go over it line by line. Please, okay, good. So the first important thing that I need to do is import the header file for this bindings. And then I'm going to import my SDK header file, right? So if I would try to compile this right now, it won't work because I haven't imported my Xc framework, right? Xcode doesn't know where to look for these files. So I'm just going to declare a module, and I'm going to declare a method that just it's called init, and it takes an API key, right? So let's say pretend this is an example of an SDK or whatever you want, or your own module. It just takes a function that takes an API key. So just to make sure that my function is called, I added a log in here. And here, since I have imported my header file, the function that I had declared on the Rust side is just available. Right? So here I have a const jar, basically a pointer, right? And I'm just turning this into a NS string, and afterwards I'm just logging it. So the easiest way to import your Xc framework is just dragging it and dropping it. So I'm going to do rebuilding finder, and I'm going to go back to Xcode, and I'm just going to drop it here in the framework section. I make sure that copy items if needed is not selected. I just want to create the reference, and I want to add it to the sample SDK target, and it's there. Now what I'm going to do is make sure that if I go to build phases, I want to link the binary with these libraries, and here you can see my SDK blah 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 framework. So let's try to compile this and see if it actually works. All right, that's good. The packager has started and my application has started. So what I'm going to do now is I'm just going to go into my app.tsx, and I have a bunch of stuff here that I don't need. So I'm just going to copy it for the sake of time, just to make this a little bit faster. So, blah, blah, blah. So, it copied. Man. Okay. Okay, so there's no magic into this. It's just importing the native modules from React Native, finding my module I have created, and then basically just calling my init function with the API key. So if I go back into my application, it cannot find it. Let's try to compile this again. Maybe I am missing. Now let me first change this into an file so that it is a C++ and not just Objective-C. Oh, I pasted it in the wrong place, sorry. Okay, so this is my header file and this is my bindings file. Okay, so now it cannot find it. It cannot find the header file from my SDK. So maybe we need to go and check here. Well, let's try embed and sign. Leave my SDK. Let me just check if what has been generated. It's just generated my SDK. So we can try like this. Good. You see, so all the small things that if you have never done this before, then you will just be like, well, but it's there. It doesn't work. Well, the problem was that the XC framework was not being embedded when compiled for the application for the simulator. So I just changed this from do not embed to embed and sign, so it can be loaded on the simulator. And I just fixed the name of my generated header file. And we can see here down in the logs, I received the API key from JavaScript. So I'm not doing anything with it for the moment. I'm just calling the Rust function, receiving the pointer, and then casting it to an NS string. And then you can see receive string from Rust, hello world. Okay, good. This is where I'm going to stop for now. There are many other things that we need to take care of, right? So one of the important things, or the selling point of Rust is memory safety, right? So we cannot just create a string on the Rust side and just pass it to C and just forget about it, right? Like we need to tell Rust somehow to take care of this. The borrow checker is right now holding into this value. So if I would call this function more times, then Rust will never let go of this object and you have a memory leak. So there are many options to do this, but this has more to do with the Rust world. And there's more information out there. So for now, I just wanted to get the binding working, everything's compiled, and it's working on React Native. Good. I'll see you in the next video where I will probably take care of Android. And just remember, I am available for work. If you need a React Native, C++, I'm also learning Rust at the moment. If you need a developer, just let me know.